in this episode.
The machine itself is awesome. The number of pieces that interplay is almost beyond comprehension.
The eyes in the sky, the airborne warning and control system.
AWACS is a revolutionary bit of kit. It's a trailblazing aircraft.
There are so many challenges that had to be overcome by engineers here.
And the groundbreaking innovations from history.
It's a major thanks to engineers that really paved the way to what we have today.
Oh, there it is. That thing is huge.
That make the impossible possible. A remote outpost in Western Germany is home to NATO's main operating base, where a specialist crew from around the world is constantly on alert. Their job, to spot hostile intruders and protect state borders that span the Northern Hemisphere.
The military are permanently on the lookout for different types of threats from all around the world. Hostile craft are in the air, on land, on sea, and they can come from all different directions. And without cutting-edge technology, protecting and defending is impossible. Hostile aircraft in particular are masters of camouflage because they can fly out of sight in valleys or behind mountains, and they can fly incredibly fast and low, all without being detected. The fundamental challenge for the military is to detect threats early so that they can react quickly and, if necessary, defend.
For over a century, engineers have been coming up with ingenious ways to improve military surveillance. By the 1930s, both the U.S. Army and Navy began developing radio equipment that could remotely locate enemy ships and aircraft. And modern-day engineers have now taken radar technology to the next level: the skies. This is AWACS. The Airborne Warning and Control System is one of the most sophisticated surveillance systems on the planet, all mounted in a specially modified aircraft, able to seek out, locate, and defend against threats, no matter how fast-moving or well-hidden.
This is a massive and highly sophisticated machine. It's carrying 4.7 tons of ingenious technology on its back, 7.6 tons of equipment in the body of the plane. That's a staggering 12.3 tons of specialist equipment, and it's airborne.
The technology behind this amazing aircraft is kind of magic. It's just a tremendous piece of engineering.
This one-of-a-kind aircraft is able to spot threats not only in the air, but also at sea. It's operated by a specialist crew of engineers and technicians, surveillance experts, and weapons controllers. Beneath the crew lies state-of-the-art signal amplifiers, the nerve center of this aircraft's most unique feature: an enormous 30-foot rotating radome, housing a 1 million-watt radar system with a scanning range of more than 115,000 square miles, an area larger than Arizona.
You are clear on engine number 2, target posted.
All right.
The advanced technology within AWACS also enables it to function as a flying command post for large and complex missions.
This incredible machine can be used to coordinate up to 150 aircraft at one time, and that's what makes it so extraordinary. There has never been an aircraft with this capability in military history. When the AWACS is in the air, nothing and nobody can hide.
Today, the crew has been sent to investigate suspicious activity due south. They'll be airborne for 12 hours.
Traffic 330.
AWACS is an incredibly complex piece of aviation equipment. The machine itself is awesome. The number of pieces that interplay is almost beyond comprehension.
There's so many aspects of this aircraft that you would normally find spread over a huge area on the ground there. Nowadays, it is all in one plane. It's an incredible aircraft.
All the groundbreaking technology that's been added enables AWACS to carry out the most complicated of missions. But creating a machine like this poses massive challenges.
So how do you mount this huge radar system on the back of an aeroplane? How do you protect against a threat that's invisible? And once in the air, how do you stay there for as long as possible?
The first challenge for engineers was to redesign an aircraft to make the eyes in the sky. AWACS is equipped with a 1 million watt radar system configured for long-range radar surveillance. And to achieve maximum coverage, the radar is housed in a 30-foot rotating radome on top of the plane. On the ground, engineers are working 24/7 on the AWACS fleet.
The aircraft is vital to the alliance here. We can do air battle management and various other activities. So the commanders regularly request AWACS support. It's an incredible aircraft.
But when flying nearly 500 miles per hour at over 32,000 feet high, ensuring the radar system functions properly is full of challenges.
The first problem is the sheer size. All that power and equipment that would normally be in a large radar tower is now going on an aircraft. On the ground, you have plenty of space for your generator and cooling mechanism, but in the air, you simply don't.
In addition to the size, the radome must be stable enough to withstand wind, vibration, and temperature, and the stresses of taking off and landing.
The radome also needs to allow the radio waves to pass through it, so there can be no internal structure that would compromise the signal.
To pull off such a complex challenge, engineers will need to draw inspiration from mankind's greatest mission.
3, 2, 1,
The Airborne Warning and Control System is a mobile, long-range surveillance and control center for air defense. To create the eyes in the sky, engineers must redesign an aircraft, equipping it with a 1 million watt radar system inside and a 30-foot rotating radome on top of the plane. To come up with this complex design, engineers looked to the pioneers of the past. The first long-range radar arrays were planted firmly on the ground. British radar systems throughout World War II were mounted on huge, heavy 361-foot towers. To come up with a solution to the problem of strength versus weight, engineers found inspiration in outer space. Kate Mulcahy is at London's Science Museum, home to one of mankind's greatest achievements.
And here it is. This is the Apollo 10 command module.
This is the actual command module that orbited the Moon 31 times during NASA's 1969 lunar program. This 3-crew mission to the Moon and back was the dress rehearsal for the lunar landings that followed and pushed engineering to the limits. Apollo 10 returned to Earth at an incredible speed of 24,791 miles per hour, the highest speed ever attained by a crewed vehicle. But to make the trip a success, NASA's engineers had to build a spacecraft that could withstand the challenges of the lunar mission.
They had to build a module so that it was light enough to get to space in the first place, but it also had to be rigid and strong so that it could withstand the stresses of re-entry as well as deceleration forces of up to 6.7 G. And finally, it had to not buckle or collapse when it actually landed. And I can see part of the solution here. This is a honeycomb lattice that's sandwiched between two thin outer layers.
In 1638, Italian astronomer and scientist Galileo Galilei observed how honeycomb-type structures in bird bones increased strength without adding weight. The principles observed in nature inspired engineers to build their own honeycomb structures.
These sheets of paper clearly aren't very strong, but if I'm to take these same sheets of paper and instead use them to make tubes like this, if I then take the tubes of paper I've made and I attach them all together, I get a honeycomb type structure. Now, if I add a sheet top and bottom, what I'll end up with is a sandwich.
The exact same amount of paper that was once flexible is now rigid.
Now, the facings on this sandwich take the bearing load. That's the compression and the tension. And the honeycomb takes the shearing load. This structure is incredibly strong. Not only can it carry one brick, but actually it can carry much more than that.
Honeycomb sandwiches allowed NASA to meet the criteria of strength, rigidity, and low weight.
This can easily take 7 bricks. In fact, it could probably take more.
But engineers still faced the biggest challenge of all. On re-entry to Earth, temperatures would reach about 5,000 degrees Fahrenheit, hot enough to melt most metals. The honeycomb was made of 370,000 individual cells. Epoxy resin was injected into each cell by hand. Engineers calculated that the resin would melt in such a way that heat would dissipate away from the inner structure.
Considering this was such a new technology, I can only imagine the thoughts of the crew as they were finally making their journey back to Earth.
3, 2, 1, lift.
The ultimate test came as the module approached the Earth's atmosphere.
Hello, Houston, Apollo 10. We are returning to the Earth. Over. Glad to have you on the way back home, 10.
The resin on the module's heat shield had burned away, leaving the layers of honeycomb and inner structures perfectly intact.
It's amazing because this honeycomb sandwich not only saved the mission, but it also saved the lives of the crew inside.
Thanks to honeycomb sandwich technology, 11 modules successfully made the treacherous journey through Earth's atmosphere and back over the course of NASA's lunar program. The NASA team had achieved the impossible. The radome structure on the AWACS radar system is also formed from honeycomb, making it light enough to piggyback on a jet plane. Lieutenant Colonel Jens Meyer oversees the radome's maintenance.
I got some honeycomb material here. Let me just show you what this really is made of. Very flexible, very lightweight. This type of material, when you put layers of fiberglass on top of it, it also becomes very inflexible, so you have a very sturdy while lightweight structure that can withstand very strong forces.
The strength of the layers that form the radome means no internal bracing is needed. And the shape of the honeycomb allows radar signals to pass through the structure, uninterrupted and without distortion.
Without the honeycomb structure, it would have been impossible to manufacture the rotodome as it is today.
Okay, let's have a look at the antenna. So we are going close, forward.
Engineer Roger Schneider services the radar assembly.
Okay.
The radome's interior is the heart of AWACS.
Up front, you see a motor who turns the antenna. It's a hydraulic motor. This makes it possible that the antenna is spinning at 6 rotations per minute. Up here, you have 3 receiver protectors and just below, low noise amplifiers.
But powering this million-watt system provides engineers with a further problem.
One challenge in transmitting at that high power, of course, is the heat that is generated by the transmitter. Therefore, we are cooling and stabilizing the temperature with fluoride carbonate, and therefore having a very stable temperature, what is important for the antenna to work as designed.
High temperatures inside could also cause the radome structure to distort, obstructing the radio waves. So the honeycomb is infused with a resin mix that helps maintain the radome's stability during temperature changes. It's the perfect environment for radar transmission.
We are able to work and pick up targets with less noise, therefore achieving a higher range.
Octane 58, Magic loud and clear.
Such a highly sophisticated cooling system is the only reason AWACS is able to achieve its mission.
33,000, passing from west-east.
AWACS is a technological marvel, but the eyes in the sky is only effective when in the air. So engineers need to develop a method to allow for extended flight time.
Refueling is an inherently dangerous problem. There's nerves every time you go up.
Flying south from the NATO air base in Germany, AWACS is on a surveillance mission over the Mediterranean. The crew is investigating a sudden spike in air and sea activity along the North African coast. AWACS is a highly specialized jet plane with a reinforced fuselage. The structure is equipped with over 300 miles of electronics and cooling systems to feed the radar assembly. And on the plane's roof, a 30-foot diameter radome is rotating once every 10 seconds, monitoring the entire Mediterranean area below.
One of the challenges involved with monitoring large areas is staying in the air long enough to gather all the information that is needed.
AWACS can fly for up to 8 hours. But for some missions, pilot Micah Redfield may need to remain in the air for longer. The only problem is, the fuel consumption is dictated by the load he's carrying.
So we can take anything from 5,000 or 10,000 pounds to 100,000 pounds if there was a mission that really dictated that much on-load.
So how do you keep a 100-ton military aircraft airborne beyond its fuel capacity? For the answer, engineers look to one of history's greatest aeronautical inventions. In Texas in the mid-1930s, brothers Al and Fred Key had their sights set on breaking the world record for the longest ever non-stop flight. They were flying a Curtiss Robin plane called Ole Miss.
Push the mixture in. Throttle is set. Area is clear. Hit the starter.
Pilot Andrew Keast flies one of the few remaining Curtiss Robin planes.
Let's have some fun. What's special about this airplane is it's a beautiful and graceful airplane as it flies. It's in its own class.
The Key brothers knew the Curtiss Robin would be the best plane to help them rewrite the history books.
The tubular design of the Curtiss Robin was a very strong design, so they were able to put a very large fuel tank in the back of the airplane for this endurance flight. And the structure of the fuselage was strong enough to support running boards on both sides of the airplane, and the pilot and mechanic would be able to go out and service the engine, change spark plugs, change oil, all during flight without having to shut it down and land.
The Key brothers had the perfect plane. Now, they needed to find a way to refuel without stopping. The ingenious plan they came up with seemed simple. Spare fuel would be carried by a plane above, and a fuel hose would be lowered to the Curtiss Robin below. But mid-air refueling would prove to be more difficult than it seemed.
I can't make it any better than that.
A fuel hose without a weight to steady it was lethal. Back on terra firma, Andrew's simulating in-flight conditions.
Here's an example of just a line with no stability device on it and how unstable it is. You can imagine what this would look like at 80 miles an hour.
Previous attempts had been unsuccessful. Fred Key was hit in the face by a hose. Another pilot tragically lost his life when he struck the propeller. The Key brothers had to figure out how to stop the fuel hose from spinning dangerously out of control.
So the Key brothers looked into aerodynamics to find a way to stabilize the fuel hose, and one of the things they come up with was a basket they put on the end of the hose to stabilize it.
Andrew's going to test the cone-shaped device the brothers came up with.
Okay, here we go for a test. So coming through 10 miles an hour, it's lifting off the ground. There's 20 miles an hour. Well, it's flying and it's just holding in there nicely. It's just very stable. 20 miles an hour, it's working.
Equipped with cone-shaped aerodynamics, the fuel hose could be managed safely at altitude and at speed. On June 4th, 1935, the Key brothers set off on their record-breaking attempt. With mid-air refueling mastered, the Key brothers were able to receive more than 6,000 gallons of gasoline. The brothers achieved an astonishing world record. They flew their Curtiss Robin non-stop for 653 hours and 34 minutes. 27 days in the air.
The Key brothers were definitely aviators of the day. They truly were test pilots. They helped engineer aerial refueling. It's a major thanks to engineers and early aviators that really paved the way to what we have today.
Modern mid-air refueling rigs use aerodynamic designs pioneered by the Key brothers. But the AWACS is much heavier than most planes, so engineers will have to take the refueling process to the next level. In 1935, the Key brothers set a world record for the longest non-stop endurance flight when they flew a Curtiss Robin plane non-stop for 653 hours and 34 minutes. The long flight was made possible by the Key brothers' ingenious use of aerodynamic designs to allow mid-air refueling. Today, mid-air refueling rigs still use designs pioneered by the Key brothers.
And you are established. Copy.
The probe and drogue system is the industry standard.
As technology has progressed, that has developed into the probe and drogue system. So having essentially a parachute at the end would stabilize the movement of the hose system, and the drogue became a much more effective tool.
Tuner 42's disconnected. And he's off to the right.
But despite the proven technology of the probe and drogue system, refueling AWACS is a much bigger challenge for pilot Micah Redfield.
A heavy aircraft like the AWACS is not as maneuverable as a smaller fighter might be, because the AWACS just simply isn't capable of maneuvering quickly enough to use a drogue-style traditional system.
I won't be able to see him, but he's coming back soon. Copy that.
Engineers had to take the refueling system to the next level, a remote-controlled flying boom. Approaching the tanker plane, Micah must use the utmost skill.
The pilots will proceed visually up to get within 50 feet of the tanker initially.
A bit to the left? Yep. Perfect.
At that point, the pilot will stabilize the aircraft and try to neutralize any aerodynamic forces that are affecting the aircraft.
40 feet. 30. 20 feet. 10 feet.
Flying on full manual control at over 300 miles per hour, just feet below a tanker filled with fuel, is one of the riskiest maneuvers Micah will ever have to face.
It does become quite complicated, and it's a very physically demanding skill for pilots to develop. It is something that takes a lot of concentration and effort.
Clear for contact. Off to the right.
The boom operator is sitting in the back of the tanker aircraft, and they have a joystick that can actually fly winglets on the boom to move into position.
Six-one contact. I'm pumping. Copy.
With almost 1,000 gallons of fuel being pumped into the AWACS every minute, the entire crew is on high alert.
The system has always been an inherently dangerous problem. There's a bit of nerves every time you go up, but you still have to be very conscious of what you're doing and what you need to do to execute safely.
Having safely docked and received thousands of gallons of fuel in midair, AWACS is ready to go.
The people who pioneered air refueling were incredible aviators and also just incredible human beings. They were figuring it out all for the very first time. It was really amazing what they were able to do, real pioneers of aviation.
AWACS can remain airborne for as long as the crew needs, but there is one hidden menace no one can see.
And high-altitude bursts would overload the circuits here and burn them.
And engineers will have to take down this invisible threat. AWACS is one of the most sophisticated surveillance systems on the planet. Able to fly at more than 32,000 feet for as long as necessary. This mission has been underway for 11 hours as the crew investigates a spike in activity along the coast of North Africa. And this extended flight is no problem for the plane or its pilot.
The rotodome additions to the airframe created a lot of aerodynamic impacts that the engineers had to consider when they were developing it. Fortunately, those engineers are very good, and when they designed the aircraft, they made it so the rotodome has negligible impact.
On top of the plane, the 30-foot rotodome houses a 1 million watt radar assembly. The radar ancillaries and cooling systems extend through the fuselage and wings. Inside, 3 technicians, 5 surveillance crew, and a tactical director manage the data. The radar system enables AWACS to see an area of over 115,000 square miles below.
The radar is delivering a lot of raw data. It's being processed onto the screens for the individual to actually assess whether an aircraft is a friendly, is a foe, whether it's a fighter aircraft, whether it's just a transport aircraft. They provide a consolidated air picture for the commanders on the ground.
But it's the invisible threat that causes the most destruction.
One of the major challenges when designing the AWACS is how to keep the aircraft flying during a nuclear war. In the event of a nuclear explosion, electromagnetic pulses are released that can disable some of the sensitive equipment on board, rendering it completely useless.
To keep AWACS safe from an invisible enemy, engineers had to look back at the biggest bomb blast of its time. In July 1962, the U.S. carried out the Starfish Prime nuclear test.
Starfish Prime was launched and was entirely successful.
Exploding a 1.4 megaton bomb 249 miles above the Pacific Ocean.
A tremendous amount of data was recorded during these events.
The blast caused a sudden and rapid acceleration of charged particles, called an electromagnetic pulse, or EMP. Similar to a bolt of lightning, the pulse was so powerful, it destroyed electrical components almost 1,000 miles away.
We do need more information on this fireball blackout.
With the threat of nuclear war still around today, AWACS must be protected from the destructive effects of EMP. Dan Dickrell is visiting a top-secret U.S. Air Force facility to find out more.
So this place is really off limits. No one gets to come here. I've heard about it, and oh, there it is. That thing is huge. That is something else.
In the 1970s, engineer Dr. Carl Baum built an EMP test facility at Kirtland Air Force Base in Albuquerque, New Mexico.
All right. Well, let's go have a look.
Decommissioned since the early 90s, the site is still a masterpiece of engineering.
Oh, wow. This massive structure is 1,000 feet long and 125 feet high, and it's the world's largest structure made entirely of wood and glue. It's called the Atlas Trestle.
Costing $60 million and constructed with 6.5 million board feet of lumber. The trestle was strong enough to support a fully loaded B-52, then the largest and heaviest bomber in the U.S. inventory.
Aircraft would taxi down 1,000 feet to the end of the trestle, perched above the ground as if it were in flight. Once we were in position, two massive generators on either side would unleash a 200 gigawatt pulse in less than a millionth of a second. That energy would be directed down these transmission wires. This pulse would simulate the EMP generated by a nuclear explosion.
The engineers knew how to generate EMP, but the bigger challenge still remained. Next, they would have to simulate its effects in flight. An abandoned Air Force base in New Mexico is home to the massive Atlas Trestle, a unique electromagnetic pulse generation and testing apparatus. Once used to measure the effects of electromagnetic waves on military aircraft. Two massive generators simulated the EMP generated by a nuclear explosion, but engineers needed to test the effects in flight.
Now, the ground can affect the EMP readings, but also the trestle itself, the structure. So the solution to this was to create the entire thing out of wood, no metal at all. These giant, large timbers, even the nuts and bolts are made of wood, and I have an example of one here. The wood is impregnated with a phenolic resin. It makes it very strong, but also EMP transparent. The combination of all of these solutions meant the EMP results would not be affected.
With the trestle itself shielded from interference and the EMP generators working at the optimum configuration, engineers could apply stress to specific aircraft components and determine how to protect flying planes from nuclear attack.
So the solution looks something like this. Here I've got two phones. I'm going to call this phone from this phone. As I dial my number, what we'll see is the radio waves go from this phone to the mobile tower, transmitted through the atmosphere, and here we see the phone call is being made. So it works, but what I can do now is I can trick this phone into not receiving the call. So I'm going to take this phone and I'm going to wrap it in this fine wire meshing. This phone is now safely encased. Okay, so let's try this again. I've got my phones. When I make the call this time, I'm going to listen. The call is being made. The radio waves are going through the atmosphere, but the receiving phone is not ringing.
The trestle engineers were using a principle first devised in the 1830s.
So we had constructed a Faraday cage. How does that work? Well, in the atmosphere, we have electromagnetic waves that are traveling through, in our case, radio waves for the cell phone transmission. If those waves encounter a barrier where the holes in that barrier are quite small, smaller than the wave itself, the wave cannot penetrate that barrier and is forced to go around. So the wave can't pass through the barrier because the hole is too small. And this principle is the same principle that is used to protect aircraft from the harmful effects of atmospheric EMP.
Throughout history, many plane designs benefited from EMP testing, making the Atlas Trestle one of the great secret engineering feats of the 20th century. Engineers have applied everything learned from the past to create AWACS.
They actually designed this aircraft being a big flying Faraday's cage here. So the fuselage made out of metal there, that will route all the energy around the precious electronics in the inside.
AWACS is engineered to be the most EMP-resistant plane possible. An aircraft structure designed and built to withstand and redistribute electrical charges. Door seals fitted with EMP-conducting gaskets. But the EMP proofing doesn't stop there.
All the cabinets inside the aircraft are also smaller Faraday's cages there, protecting all the electronics inside even further.
And the sensitive radar equipment is shielded too.
There are also filters in the lines from the antennas, filtering out whatever spikes of electromagnetic energy is coming through there.
But there's still one more challenge: the plane's windows. Glass doesn't stop EMP, so the windows are laced with a fine wire mesh. The holes are smaller than the electromagnetic waves, so they won't pass through it. And the crew can still see out.
Left, you can do 180 left, easy, inbound CP.
Okay.
The runway is set.
Yep. 50, 40, 30.
The mission today has analyzed a huge amount of data to build a clear picture of activity across the Mediterranean, in and out of North Africa. The classified information has been relayed directly to Allied NATO forces.
Excellent, NATO 11.
No wonder AWACS has been declared the most significant single tactical improvement since the advent of radar.
It's incredible how people manage to overcome all these challenges, putting radars in here, electronic systems here, inertial navigation systems. This aircraft is just a tremendous piece of engineering, and I'm actually very glad that I'm allowed to help maintaining it.
AWACS has truly pushed the boundaries of engineering.
I have to say, I love this system. It's one of those aircraft you really have to love as an engineer, because there are so many challenges that had to be overcome by ingenious engineers here. For me, it's an incredible aircraft.
By learning from early innovators, adapting, upscaling, and conquering countless challenges, engineers have created a plane like no other.
Those moments that you can stop and step back as you walk out to an airplane and you see it, you really appreciate how much has gone into aviation, and you get a little of the joy of why you started flying in the first place. So I enjoy it. It's a great experience.
It has taken decades of innovation. This is a triumph of engineering that has to be seen to be believed.
The AWACS engineers have succeeded in making the impossible possible.